Welcome to Learn Kubernetes from a DevOps Guru, where you will learn the ins and outs of the exciting container orchestration technology, Kubernetes. My name is Basit Mustafa, and I'll be your instructor for the course. In my 10-year career at IBM, and now at the 4 years of the company that I founded from the start, I've focused on building production global scale technology systems, and leading and mentoring the technical teams that make them a reality. I've worked through the evolution of production systems from client-server technologies to virtualization to containerization and now to container orchestration. That's why I'm excited for you to discover the ease with which Kubernetes lets you create performant, scalable, reliable, and robust applications in this course. We'll start with the foundations of Kubernetes as a container orchestration and move through practical examples that will grow your skills in how to build performant, reliable, and robust systems using Kubernetes on your laptop all the way up to large production, high availability systems in the world's largest public cloud. We'll examine the ins and outs of actual deployments on real clusters, and you'll gain experience and wisdom that can only come from doing it in real life. I'll be with you every step of the way to point out pitfalls, gotchas, and other things you can only get from experience. I'm excited to be a part of the next step in your DevOps journey as we explore Kubernetes together. Welcome to Master Kubernetes. In this course, we'll explore Kubernetes, the leading package in one of the most exciting and lucrative areas of computing technology today, container orchestration and deployment. We'll focus on hands-on learning, but first, let's explore the trends that have given rise to containers, the need for container orchestration, and how that has created the space for Kubernetes to rise to dominance and growth. The growth of technology into every aspect of our lives and days has created immense demand on software. The companies and organizations that sell and deliver products based on software or just use software in their businesses. This really is nearly any business and anyone who doesn't live entirely off the grid. This pressure has spurred innovation and standardization, and the needs and stakes are so high, it has fundamentally changed how software is developed and deployed into production. But this evolution isn't without precedent. Could you imagine the world's economy relying on methods like this for the trade of goods? There would be no way you'd get your new iPhone in time. Now we take it for granted that shipping containers efficiently move between different modes of transportation, different ship owners and shipping companies, and they've standardized, ubiquitous, and available anywhere in the world. Almost always, no matter what it's in, if it fits, it ships. Modern software is becoming quite similar. As software systems become more complicated, this complication has driven software to be divided into smaller pieces such as microservices. Whether they're called microservices or not, these smaller pieces of software each need to be packaged, built, deployed, and accessed by other pieces of software around them to function as a total system. These small pieces of software can be deployed into containers that allow them to run on the same machine, virtual or real, but making it appear to the software that it's the only process running. Here's where we depart from the shipping container metaphor a bit. While a shipping container's sole job is to keep things contained within itself, typically interesting and useful software depends on other software around it to do its job. Here is where the need for container orchestration is born. There are definite benefits in keeping logically distinct software separate from each other. You can develop, deploy, scale, and maintain each small piece without too much fuss between the other parts of the system when it's not all in the same module. However, at some point, different parts of your application likely need to communicate with each other to do something interesting. For example, an API may need to communicate with business logic. It needs, in turn, to access information in a database. Containers themselves keep logically distinct pieces of software separate so they can be built, deployed, maintained, managed, and scaled on their own without unduly affecting other parts of the system. Container orchestration, on the other hand, defines how these containers interact as a system, the needs between each other, and how they come together to a performant, manageable, reliable, and scalable system. It is currently safe to say that Docker is the dominant leader in both technology and in adoption in containers. While others exist in the space, their dominance is so great When you mention containers, it is almost synonymous with Docker. Other players exist in niche applications, and some movement around standardization is occurring. Although it is nascent, the Docker file standard is essentially today's standard, and Docker repositories define the dominant way of hosting versions of a container between developers and between systems that need to use them, such as orchestration systems like Kubernetes. Since container orchestration is a much newer space, only growing since the adoption of containers, the technologies are newer and still evolving. However, Kubernetes is quite advanced, and with Amazon Web Services finally joining its competitors in embracing Kubernetes, it now has the backing of nearly every major player in cloud computing through the Cloud Native Computing Foundation, also known as the CNCF, the organization that now governs Kubernetes. It has essentially become the de facto standard, especially now that it's nearing alternative or competing technology, Docker Swarm, Docker's solution to container orchestration, has now announced support for Kubernetes-style configuration and processing. It is clear that Kubernetes is now the de facto standard, if not the acknowledged standard, in the industry in container orchestration. Containerization changed how software was developed and packaged. Container orchestration is changing how containers are deployed into bigger, useful systems. From here on out, we'll focus on how to use Kubernetes as your framework for container management using Docker containers. In the next lecture, we'll focus on the growth, lineage of, and why the market has chosen Kubernetes. In the previous lecture, we discussed how the evolution of deploying software modules into standardized packages that could run nearly anywhere was called containers, or containerization. You may recall that this movement towards containerization has created a new need to define and manage the life cycle of these containers and how these containers interact with each other to create a larger, interesting, and useful software system. The de facto standard for container orchestration is now Kubernetes. Kubernetes was born out of a project of Google's internal need for container orchestration. It was first announced in 2014 and has grown into a mature product, currently at version 1.8, with support and growth in the enterprise and most major cloud providers. Kubernetes, as a product, is governed in standards and deployment and development by a public process led by the Cloud Native Computing Foundation, also known as the CNCF. Much like the Linux model, Kubernetes has itself been repackaged into distributions with support and other commercialized offerings by large vendors, many of whom themselves are members of the CNCF, with many of the changes and improvements that they make going back into the open source project. Kubernetes enjoys a major lead in technology maturity and adoption for a variety of reasons. First, Kubernetes and its predecessor, Google Borg, go back to the very beginning of container orchestration. It simply has a head start on solving a very complicated problem. But that's not enough to sow a large advantage, of course. That dovetails with the second. Kubernetes and the people around it, especially its founders, have taken this organizational knowledge and preserved and grown it through the CNCF and a public stewardship process that allows Kubernetes to grow unlike proprietary technologies. Kubernetes has been free to be bigger than any one vendor's market share and has gained the trust and commitments of its users and the open source community at large, in large part by avoiding vendor lock-in, but allowing access to the kind of support and assured quality large vendors can offer through their own distributions. That is not to say that Kubernetes was or is without its competitors. Docker, the company that created Docker containers themselves, that Kubernetes uses by default, has its own orchestration offering, for example. However, as it relates to Docker Swarm or even Apache Mesos, another mature orchestration project, Kubernetes has several distinct advantages at the moment. First, its lineage has given it quite a lead time in both time and pedigree. It never hurts to be born at Google, solving problems at Google scale. Second, it's not just achieved critical mass, it's actually grown to sustainability. And the CNCF organization provides some permanence to this, especially as every major cloud vendor and many major software vendors have joined the organization. As for the code, just look at the commits, follows, and stars of the various Kubernetes projects. They speak for themselves. Third, Kubernetes offers auto-scaling that continues to mature and does not introduce provider-specific details, but lets you leverage many cloud providers' implementation by abstracting them intelligently into common configuration files. This makes for an ease of deployment across hybrid clouds or public clouds or any type of deployment infrastructure. Kubernetes is a technology and software package you can run on your laptop, your own server hardware, your data centers, cloud providers, or a combination of them all if you'd like. In the next lecture, we'll discuss where to get started, how you can set up Kubernetes on each, no matter where or what path you plan to choose or need in your particular application. In the previous lecture, we discussed how Kubernetes can run nearly anywhere Linux does, on your laptop, your own server hardware, a cloud provider, or a combination of them all. In this lecture, we'll discuss with more specificity how and where Kubernetes is deployed. Kubernetes has a healthy ecosystem that carries with it many advantages. As it relates to setup and where Kubernetes lives, this means many people and companies have created both formal and informal support for Kubernetes use cases for nearly anyone's needs. For evaluating and learning Kubernetes, many people choose the Minikube distribution of Kubernetes. It sets up a Kubernetes cluster locally on any modern macOS, Linux, or Windows machine. It is not suitable for production by any means, but quite friendly and favorable for development and evaluation needs, as changes are quickly and easily propagated onto a local instance of Kubernetes without any major networks to slow you down. For larger development or staging work in production, Kubernetes can run on bare metal hardware or on cloud providers. Many cloud providers even provide a Kubernetes offering, which takes care of many of the more menial administration, configuration, and other tasks associated with running a Kubernetes cluster for you. Google Cloud Platform and Azure offer mature Kubernetes offerings that handle setup, management of your Kubernetes clusters on their cloud with ease, even through a friendly web interface designed and integrated with their cloud consoles. Amazon is rumored to have one of their own in development, or to bring Kubernetes compatibility to their existing Elastic Container Service to do the same. Regardless of where and how you run Kubernetes, you can always elect to stand up your own Kubernetes cluster on any cloud provider's virtual machines if they do not offer a Kubernetes service, or if you'd rather not use theirs. However, most managed Kubernetes offerings in the current marketplace provide a good value for many cluster use cases. Amazon does not yet offer a Kubernetes service, although with their recent introduction into CNCF, it is all but assured that one will be coming soon in some form or the other. Running Kubernetes on Amazon Web Services requires the user to set up Kubernetes on virtual machines and configure networking either on their own or using the CNCF-managed KOps deployment toolset. Using KOps whenever possible is highly recommended, as it reduces error, simplifies the work, and maintains consistency. Naturally, as the birthplace of Kubernetes, Google Cloud Platform has mature support for Kubernetes as a managed software offering through its Google Container Engine product. As you'll see later in this video series, Kubernetes setup requires a master, a few data stores, and the like to function. Google Cloud Platform's Container Engine offering abstracts these away and provides a management interface in their cloud console for these items. Of course, you can always set up your own cluster on bare virtual machines too. Manually or using KOps, however, if the economics of Container Engine are reasonable, it's always wise to consider their managed service to avoid having to run and maintain certain parts of your Kubernetes infrastructure. For developing and testing applications on Kubernetes, and especially training, it rarely makes sense to stand up a large Kubernetes cluster in the cloud. So Minikube has been created to allow you to run the actual Kubernetes code locally on your machine to avoid the complexity, expense, and slower response time of a full remote cluster. We'll use Minikube in this video series almost extensively and exclusively for just this purpose. Minikube is well supported for development testing, however, it is not a production technology. It runs the actual Kubernetes codes. It is not emulation. However, running Kubernetes locally defeats many of the purposes of container orchestration and cannot be relied upon for production workloads. But it is very convenient for training and evaluation, so we'll leverage it extensively for this, as it excels in this area. The previous 3 lectures have focused on setting the stage for why containers and container orchestration are so important. By this point, you may be wondering, with software dedicated to such large tasks at such a large scale, how does one get started and interact with it in a manageable, easy way? Luckily, there's a very good answer to this question that's easy to approach and easy to get started with. As we discussed in the last lecture, this is what Minikube is all about. A distribution and package of the actual Kubernetes code that runs in an entire Kubernetes cluster on your laptop. Remember, Minikube isn't something you'd want to use in production or even staging for an application. What makes it great for training, development, and learning makes it quite useless for production. It's a great way to get into Kubernetes quickly, easily, and without the headache and hassle of a number of other things that are required for production use. Let's get started by installing Kubernetes. But first, make sure you have a Linux machine with the latest version of VirtualBox installed, or a Mac with the latest version of VirtualBox or VMware Fusion. As we set up Minikube, take notice of how we interact with it, the patterns of the commands and the like, how they're structured, for example. These should be pretty familiar, if not identical, to how you work with full Kubernetes clusters. Because remember, Minikube is the actual Kubernetes code, and we will use the actual Kubernetes command line tools to interact with it just as if it was a full production remote cluster. As we've mentioned before, Minikube requires Linux or Mac machines capable of virtualization with a hypervisor installed. On Mac OS, this can be any number of hypervisors, such as XHYVE, VirtualBox, or VMware Fusion. On Linux, this can be VirtualBox or KVM. VirtualBox is by far the most popular and is available at http://www.virtualbox.org. We'll start with installing a package called Kubernetes CTL. This is the command line control tools for Kubernetes clusters. Whether it's a Minikube or a full-blown cloud-hosted cluster, you'll use this command line package to interact with your cluster of choice, including the Minikube cluster we're setting up today. Then we'll actually install Minikube and go through a few basic commands on how to work with it. As we dive into our first hands-on example, it's time to discuss a bit of detail as to how Kubernetes organizes concepts and a bit of terminology, so this will all make sense. First, a central concept in Kubernetes is the deployment. It is a large, general, high-level construct that groups together the various parts of an application. You can, for now, consider a deployment to be akin to an application that you'd like to deploy, thus the name deployment. Second, deployments have pods. A pod is a group of one or more containers for an application. A pod is an instance of a container image, and there can be many of them in a deployment as needed. Third, services are endpoints that expose network ports to the outside world and are mapped to a port on a given pod for a deployment. This is how end users or intermediate services might access the services exposed by your pod or your container image you're looking to deploy. There are various types of services that we'll get into later in the lecture series. For now, just consider services as network ports that expose an application. First, let's install Kubernetes CTL, the command line utility used to interact with Kubernetes clusters. You'll use this tool for both our local Minikube instance and any remote clusters you may manage or interact with. These installation instructions are built against Kubernetes 1.8 and guide you through manually installing and downloading the Kubernetes CTL executable and installing it into your path. If you're familiar and comfortable with your specific operating system's package manager options, it may be beneficial to use such a route to install and maintain the latest version. For example, on macOS, the Homebrew Package Manager provides simple and straightforward installation and maintenance of the Kubernetes CTL package. and several unofficial Debian sources exist for use with the apt package system on various Linux distributions. If you're comfortable and aware of how to use your operating system's package manager, we recommend using it to install and maintain the kubectl command set. You can skip these installation instructions if you'd like to use your operating system's package manager. If so, rejoin us on the next slide for testing your installation and moving on to Minikube. We'll begin by using Google to find the appropriate documentation. Let's Google install and set up kubectl. The first hit's exactly what we're looking for, the Kubernetes documentation on setting up kubectl. Let's go here and scroll down to the area that includes the URL to download for our platform. We'll choose Linux. Let's copy the URL and the command all at once so we don't have to retype it. With this copied to our clipboard, we'll now begin installation. And remember, we copied the URL, but you're also free to copy subsequent commands out of the Kubernetes documentation if you'd like to avoid retyping them. We'll start by downloading the appropriate package for our operating system, in this case, Linux. Once the download's completed, we'll make it executable. This step is not required on Windows. Now, we'll finally copy it into our path so it's executable no matter what directory we might be in. Now that you have kubectl installed, let's check to make sure it works properly. At the command line, type kubectl space version. It should output something similar to what you see on the screen here. Your version numbers may be different, and your git commit numbers are certainly going to be different. But as long as the command was found and it returns something similar to what you see here, you can be relatively confident that your install went well. Let's run this command on our Linux instance to see what its output looks like. Don't be alarmed at the error. This is just because we haven't set up a Kubernetes instance. Now that we have kubectl properly installed and working, let's move on to installing Minikube. Again, these installation instructions are built against Kubernetes 1.8 and guide you through manually installing and downloading Minikube and installing it into your path. If you're familiar and comfortable with your specific operating system's package manager, again, we recommend that you use that option to install Minikube. On macOS, the Homebrew package manager sometimes provides the Minikube formulas, and on unofficial Debian sources exist for use with the apt package management system again. Once again, let's consult Google for the appropriate page. We'll Google installing Minikube release. Again, the first result in this case is what we're looking for, the releases page on GitHub from the Minikube project. Let's go there. Let's scroll down on the latest release to the installation instructions and URLs. Again, let's copy the appropriate one for our platform to avoid having to retype it. Remember, you can continue to do this for subsequent instructions if you'd like to avoid retyping them. With this on our clipboard, let's move on to the actual install steps. We'll use the appropriate command to install Minikube for our operating system. Now that you have Minikube set up in your system, let's go through some basic Minikube commands. Before we get started, remember, you can copy and paste these commands from the text lecture at any point. Each one of these commands is available for you to copy and paste in this lecture and in subsequent examples. To begin, let's actually start our Minikube cluster by typing minikube start. It will take some time to download the various images and get the cluster started on your machine. If your machine's as slow as mine, you may want to go get a beer. You'll notice the kubectl is configured to use the cluster. Minikube does this for us automatically. Let's use kubectl to actually deploy the Hello Minikube sample application. We use the kubectl run command to deploy a sample image to our Kubernetes cluster. This command is worth noting. We'll use it extensively throughout this example and in future lectures. This command provides a simple and quick way to run a given Docker image on your Kubernetes cluster. While you may want to package a Docker image with more sophistication for full orchestration capabilities, the kubectl run command provides you the ability to quickly and in a straightforward way run a given image on a Kubernetes cluster when you need to. It's a useful command that you should note. We'll go further in depth about the usage of the kubectl run command in further lectures. Now that it's deployed, let's expose the Minikube sample application using the service command. This command will take the application, which is running locally in our Kubernetes cluster, and allow external IP addresses to access it. You may have noticed the use of the word deployment. In Kubernetes, a deployment is any set of resources that deploys a container, an application, a set of containers, or pods. We'll go further in depth as to what deployments are and how to work with them later in the course. The kubectl expose command is another command that you'll likely end up using quite frequently throughout your time with Kubernetes. Take some time to understand exactly what it does. In this case, we're exposing the deployment hello minikube with a service of type node port. There are a variety of types of services that are available. Specifying a node port allows us to have an external IP address connected to the port on the container that we just deployed using kubectl run. Other types include cluster IP, which is a private IP not available to the external world, and load balancer. Load balancer requires external functionality from either the hypervisor, the cloud provider, or the host upon which Kubernetes is running. We'll get into the specific types and other varieties later on in the course. You'll see the service was created. We can use the getpod command of the kubectl command line tool to see the status. It's running, has no restarts, and has been running for 46 seconds. We can now access the cluster and actually access the data on the service using the curl command. You'll notice in this case, we used the Minikube service to be able to get the URL of our pod. The output, as we expected, gives us an HTTP response. And finally, when you're done with the deployment, or no longer need a deployment, or would like to replace it, you can use the kubectl delete deployment command to specify a deployment for deletion. You can also use the Minikube stop command to stop your local Minikube cluster and free up any resources when you're completed. In the previous lecture, we used Minikube to deploy a sample application to verify that we had our local Kubernetes cluster installed properly. By now, you're probably wondering, what exactly is the application that we deployed? How does Kubernetes know which Docker image to pull? How does it know what to do with that Docker image? How does it know how the Docker image works together? How does it know how it scales? And how does it know how it fails? These are all very good questions. We'll start at the beginning. Your first Kubernetes application, a very simple deployment of the Tomcat application server. We'll look at how deployments are described and how we can deploy them to Kubernetes. So what does a Kubernetes application look like? Remember, deployments are the central metaphor for what we consider apps or services within Kubernetes. Deployments are described as a collection of resources and references. Deployments tell Kubernetes what Docker containers are interesting to us, describes a little bit about them, and how they work together, what's required to keep them healthy, and what to do when they may become unhealthy. Deployments can take many forms based on the type of service being deployed. Whatever form they take, they're usually described in a YAML format. You can store this deployment in a file for replication across many Docker containers, across many Kubernetes systems. However complicated they get, ultimately, deployments simply describe the containers used in an application, how they work together, and the care and feeding of them. Deployments, as you can imagine, can get relatively sophisticated for complicated applications, but let's keep it simple and start with something small and understandable. A deployment of the Tomcat application server. In this example, we'll deploy the Tomcat app server using the official Docker image. Our key tasks will be like any deployment you might plan, no matter how small or how large. First, we'll define the deployment, what containers we use, what services those containers might offer, and where they come from. Then, we'll expose the services to the world. What TCP ports and what HTTP services are defined in the containers, and where to reach them. Finally, we'll take that configuration information and we'll deploy it to our cluster. The first step is to define the deployment. The most simple deployment in Kubernetes is a single pod. Remember, a pod is an instance of a Docker container. Deployments can have any number of pods required to get the job done. They can range from one instance of a single image, like we're doing today, and grow to hundreds of images of different types. The most simple deployment simply has one pod. No redundancy, no separation of services, just one pod deployed to Kubernetes. The source files for both this lecture and subsequent lectures are available on GitHub. If you're familiar with how to use Git, GitHub, and associated tools, feel free to clone the repository on your own. If you're unfamiliar how to do it, follow along and we'll download the appropriate tools and do it together. The GitHub repository is available via the web at github.com/jleetutorial/Kubernetes-demo. If you're going to clone this on your own, feel free to go ahead, clone it, and join us in the rest of the example. Otherwise, open a web browser and head to this URL. There are a few ways that you can access this source code and save it to your computer. We'll use GitHub Desktop. Perhaps you have it installed and perhaps you don't. Whether or not you do, click on the green Clone or Download button, where you're presented with a choice. You are free to download a zip file of the repository, which doesn't require any extra software other than unzip in order to access the files. We're going to choose Open in Desktop. When you click Open in Desktop, it will prompt you, if you don't already have it downloaded, to download the GitHub Desktop program. In this case, we'll download it for macOS. Once the download is completed, open the file, install it appropriately for your given operating system, and open the program. Once GitHub Desktop is installed and open, go to the File menu and click Clone Repository. Ensure that the URL tab is selected. Choose a local path to where to download the files. And type or paste the URL of the repository. Remember, that's http://github.com/jleetutorial/Kubernetes-demo. Click Clone, and this will copy the repository files to your system. Those files are now available at the directory you selected initially in this dialog. Let's start with the text editor open with a blank deployment.yaml file. We'll define a deployment so we can send it off to our Kubernetes cluster to understand how deployments and pods work. Now would be a great time to locate the files we most recently cloned from the GitHub repository and open the file named deployment.yaml in the Introduction to Kubernetes /your first K8s app directory. The goal of the deployment.yaml file is to provide Kubernetes with the basic information of what the application needs to do, the resources required to accomplish it. There's a wide variety of robust tools available to define how pods fail, how pods stay healthy, and what to do when they're unhealthy. We'll go over the most important aspects of the deployment YAML file. If this looks a little intimidating, don't worry. There are only a few aspects of this which are key to understand at the moment. We're going to go in depth in future lectures about items like metadata, labels, selectors, and the like. Right now, the important things to note are the image name, the number of replicas, the container port, and the name of the application. We'll go through each of these individually. We'll explore the other items in depth in future lectures. Right now, the key items to review and retain are the ones that we're about to go over. For now, we're going to keep it simple. We're going to define a deployment named tomcat-deployment that only has one replica, so one instance of one Docker image. This image is named Tomcat version 9.0. If we don't specify an external repository, Kubernetes will default to the public Docker hub. Finally, we let Kubernetes know that the Docker container Tomcat version 9.0 exposes a port 8080. This is where the Tomcat application server will listen by default on the Apache supplied image. You might remember from our previous lecture that we have to expose any ports in our deployment to the outside world. For that, we'll use the Kubernetes CTL command, similar to what we did when we were testing Minikube. We'll use the Kubernetes CTL expose deployment command to expose our service named Tomcat-deployment as a node port. Don't worry about the various types of services and what they might be. In this instance, node port tells Kubernetes that we'd like to export or expose the container port of 8080 in our previous file to the external world on an external port. Let's see the details of how this works. First, let's start by verifying the deployment.yaml is proper. Looks good. We'll use the Kubernetes CTL apply command to take the directives from this file and apply it to our cluster. You'll see that our deployment was successfully created. The next step is to expose the deployment as a service. The Kubernetes CTL expose command will create the actual service and explore it to the world. In order to find what port it was created on, we'll use the minikube service with the name of the service --URL command. This will provide us with the URL, including the port number, that we can access our given exposed service on. Copying this URL, we'll use curl to access our local service. As you can see, we'll get the HTML of the default Apache Tomcat welcome page. We can verify using this tool that our service is indeed working. Let's review what we did here. First, we defined a deployment.yaml file that indicated what image to use and what services that image exposed. Then, we mapped those exposed services from the container to the outside world. Next, we asked Minikube what port it chose to expose to the outside world. Finally, we verified using the curl command that we indeed could access our service at the given port. As you've probably noticed, the Kubernetes CTL command is relatively important in managing Kubernetes. Kubernetes CTL provides access to both local and remote clusters and is essentially the primary gateway to interacting with any Kubernetes cluster. Since it's the primary command line access tool, it's important to get to know it well. By now, you've used it to deploy some data and deploy a Tomcat deployment to a cluster. However, you can use it for a variety of other methods too. We'll go over the most common Kubernetes CTL commands here. Kubernetes CTL commands all share a relatively similar format and command set. Notice the patterns between the commands we'll review here and throughout the course. The Kubernetes CTL getpods command lists all pods in a namespace. If we were to take our current Minikube setup and run Kubernetes CTL getpods, we would have one single pod listed, the Tomcat deployment that we deployed in the previous lecture. This command provides the state, how many pods are available, restarts, and the age. Let's run Kubernetes CTL getpod on our local minikube. You'll notice that our Tomcat deployment container, actually pod, is right there. Don't worry about the other two, those are images I had running for later examples. Let's cut and paste the name of that pod for use in the next command. Copy that to your clipboard. If we'd like to get more detailed information on a pod or pods, we can use the Kubernetes CTL describe pod command. If you don't provide this command a pod name, it will provide detailed information on every pod in the namespace in the cluster. If you provide it optionally, the name of a pod, it'll only provide data on that specific pod. Let's use the Kubernetes CTL describe pod command and the name of the pod that we've already copied to our clipboard to get detailed information about the Tomcat deployment. As you can see here, we have a wide variety of detailed data specifically and only about the deployment for our Tomcat. Hopefully you remember the Kubernetes CTL expose port command. Remember, Docker containers can expose a specific port. We have to take that port and tell Kubernetes to expose it to the outside world. Using the expose port set of commands in Kubernetes CTL, we're able to name a deployment, a pod, or a service, and expose it to the given world at a given port or a random port that Kubernetes CTL chooses. We're also able to define what type of service this is. Is it an internal-only service, also known as cluster IP? Is it an externally available IP address, also known as node port? Or should we use a function of a load balancer? Those are more advanced usages we'll get into later in the lecture. However, using the type argument, we're able to specify what type of port we're trying to expose. Next, the Kubernetes CTL port forward command provides you with the facility to forward a port from the local machine on which Kubernetes CTL is running to the pod on the remote host that Kubernetes CTL is connecting to. In our current case, since Minikube is already running on our system locally, this really doesn't seem to do much different from Kubernetes CTL expose. However, when you're dealing with a remote cluster and simply need to map a local port on your machine to a remote port on a given pod or container, this can be quite useful. The Kubernetes CTL attach command allows you to attach to a pod to view its output. It attaches to a process that is already running inside an existing container. That's important to note, especially as we go over the next few commands. Kubernetes CTL exec will execute a command within a container. This is a very useful command for debugging and understanding what might be going on inside your containers, as it allows you bash access to containers that may not otherwise have interactive facilities. The -I and the -T options are relatively important. When running kubeexec, exec, you're able to interact directly with the process you run, for example, bash, if you specify the -I and the -T options. Look at the sample output. Understand what is happening here, because this is a command that you may use very frequently when debugging or creating complex deployments. Kubernetes CTL exec -IT followed by the name of the pod, followed by the command you'd like to run. In this case, bash provides us with interactive shell access onto that container. Using interactive shell access, we can then introspect processes and other items available inside that container that we otherwise would have to use other methods, such as log analysis, to get after. Let's use the Kubernetes CTL getpod command to copy the name of our existing Tomcat pod to the clipboard. Let's use that name to use the Kubernetes CTL exec command with the -IT options. That way we can interact with it using the standard in as a TTY to run the bash command. We now have a bash shell within our given pod that we specified, our Tomcat pod. Remember, Bash isn't the only command you can run. You can run anything that's executable within that Docker image specified in that pod. However, it seems to be the most common and most useful way of using the Kubernetes CTL exec command when debugging pods. Kubernetes also provides a similar set of facilities to label pods for classification either through automated processes or for manual bookkeeping. Using the Kubernetes CTL label pods command, we're able to set key value pairs on any given pod. This command updates the labels on a given resource. For example, here we're labeling our Tomcat deployment pod healthy equals false. Finally, the Kubernetes CTL run command provides us with a quick and easy way of running a given image on our cluster. You'll remember we had to define a deployment file that defined a pod that pointed to a Docker image to get our Tomcat deployment to run on our cluster. While that certainly is the preferred method of deploying production applications, in certain situations, you may want to run a particular image on a cluster relatively quickly and without having to do it in a replicable fashion. The Kubernetes CTL run command can be particularly useful in that case. You can provide it with an image to run, a port to expose, and other options and more advanced usage are also available. Let's use the Kubernetes CTL run command. In this case, we'll use the Kubernetes CTL run command to run a copy of the popular Hazelcast server. Using Kubernetes CTL run Hazelcast, giving it a name, Hazelcast, specifying the image, Hazelcast, and a port to expose, 5701, gives us the ability to create a deployment with one command. Let's use the Kubernetes CTL describe pod command from earlier to describe the pods running on our minikube. If we scroll up through some of our other pods, for example our Tomcast pod that's already there, we can see that the Hazelcast pod has been deployed. We were able to do that with a single command instead of having to define a deployment simply by hand. This is a convenient tool for a quick administration. These commands are simply an example of a wide variety of powerful commands that are available to you through Kubernetes CTL. We'll go into more in depth further in the lecture. However, it's good to keep these two references in your bookmarks as you explore Kubernetes. First, the Kubernetes CTL reference for the latest version of Kubernetes. And second, a Kubernetes CTL cheat sheet that provides shortcuts to commonly used patterns in the Kubernetes CTL commands. Remember, Kubernetes CTL exposes nearly every aspect of the Kubernetes API through that command line tool. It's powerful and will be your friend, and mastering it will make your journey into Kubernetes all that much easier. However, that's no need to fret about rote memorization. The more important aspect of Kubernetes CTL, much like anything else, is to understand what it can do for you. The documentation and reference will always be there to provide you specific details on how to do it. At this point, simply understanding what is available to you within Kubernetes CTL is going to be the most powerful tool and the most powerful area to focus on. In previous lectures, we've gone through deploying applications to our local Kubernetes cluster running on Minikube. We type a command or send a small configuration file, and the app is running. Seems pretty simple, right? Well, that's how it should be. Kubernetes is designed to keep you productive and your systems performant by abstracting a lot of complexity into higher-level concepts which are very easy to work with. But if you're anything like me, the first time I saw the magic of Kubernetes in action, I was very curious as to what was going on under the covers that reduced all of this work to a single command. Understanding this is not only fun for curiosity's sake, but knowing what happens when you execute a command and deploy a workload to Kubernetes is critical to becoming an effective Kubernetes user, operator, architect, or developer. It can also help you troubleshoot things when the inevitable problem pops up. So, in this lecture, let's look at how Kubernetes is architected at a high level. Don't worry about the individual component details quite yet. We'll go into each later on. The key thing to understand is what each component does, not necessarily or exactly how it does it for now. In Kubernetes, the task of managing containers, where they run, the nodes upon which they run, and the like is handled by the Kubernetes runtime based on input from you in your deployment file. You've seen some simple deployments up to now, and we'll get into more sophisticated ones soon. In Kubernetes, the master, or masters, you can have multiple masters for reliability and scale. We'll get into that later. The masters control any number of nodes. These nodes are individual machines that run pods. End users then, through services we declare, you may remember doing this in the previous example, access our application directly on the nodes. Don't worry about each individual component inside the masters and nodes for now. We'll go over each in turn later. Just take away from this that the masters control a variety of nodes and the pods running on them based on your deployment. Since containers and container orchestration technologies de-emphasize the role of the individual system, whether that's a server, a VM, or even a container, it can be difficult to get a starting point when exploring Kubernetes architecture. You'll remember the pod and deployment are relatively important concepts in Kubernetes from previous lectures and examples we've worked through. But let's think a little bit lower level for now and start with a familiar concept, the server or the virtual machine. In traditional architectures, it was usually the center of the universe. In Kubernetes, they're still quite important. They're called nodes. They used to be called minions, so you may see that in some older documentation, but now we refer to them as nodes. A node is a worker machine in Kubernetes. A node can be a VM or even a physical machine. Each node, regardless of what it is, has the services necessary to run pods and is managed by the master components. We'll discuss these later. Remember, masters just decide where to run your application. Kubernetes can consist of any number of nodes. It varies depending on your needs. We'll get into how you specify how many to run, what types to run, and how Kubernetes chooses what pods to run on what nodes and the like later. Don't worry about those details for now. But just remember, each node has a common set of services at the very least, regardless of what pods it may be running, that allow the master to send it work to do. These include Docker, a service called Kubelet, and a service called Kubeproxy. Kubelet watches and manages processes on an individual node. You can think of it as the supervisor for that machine. It has one job. Given a set of pods to run from a master, make sure they're running. Kubelet runs pods. Kubeproxy is the glue on each node that makes sure the network services exposed by each pod on the node can be accessed as defined in the deployment. You may recall when we set up a Tomcat service, we created a node port service to allow the outside world to connect to it on port 8080. Kubeproxy was the glue that made that happen. Let's review how this all fits together. First, you deploy an application to Kubernetes. We've done this before. Initially and internally, the master will evaluate your deployment descriptor and decide where and how to run it. It will direct Kubelet on the appropriate node or nodes, depending on if the deployment asks for multiple replicas, to run the pods. Second, you define a service so users can access it. We've done this before too. The master will create connections between an external load balancer and external IP. For example, if you're running on a public cloud, it will direct the Kubeproxy on each pod to connect to this given API or service, and the pods on each node. Finally, end users can access the services appropriately, as the load balancer will decide which pod to send it to based on the configuration created by the master during the deployment. Again, understanding this overall orchestra is more important than understanding individual instrument in it for now. In the previous lecture, we alluded to the fact you need not run only one instance of your pod. Whether it's for scale, to meet more demand, or for reliability, to have backup workers in case one or many die, replication is an important cornerstone of Kubernetes. Kubernetes supports scaling through replicating pods on the same or multiple nodes. But before we go into how this works, let's explore how applications should be designed to scale in Kubernetes. Many paradigms exist for effectively scaling an application. For our purposes here, we'll categorize them into stateful and stateless applications. Stateful applications store client data generated in one session for use in the next session with that client locally. The effect of this is to essentially lock a client session to a given thread or instance of an application on the server. If that server process dies, client state is lost. It is also the only one who knows what state that user's data is in. All subsequent requests must come to it. Stateless applications, on the other hand, update a centralized data store, such as a database, with the result of a single operation, so the next client session or operation can be handled by any thread or instance of the application. Kubernetes supports both patterns. However, it is a best practice to create stateless applications whenever possible, and leverage replication without having to use stateful replication mechanisms. Architecting applications varies by programming language and framework, and it's beyond the scope of Kubernetes. Many great resources on software design exist that discuss the different approaches to designing stateful or stateless applications. For now, let's assume you're working with a stateless application so we can focus on how Kubernetes handles scaling through replication. Kubernetes gives you a variety of options to define how a pod should scale. By far the most robust, flexible, and frequently used is setting the replica options in your deployment. It's what we'll do today. Just for the record and for your knowledge, you can also define a replica set, deploy multiple bare pods, define a job. This is useful if you're doing a niche form of bash processing, or a daemon set if you're looking to replicate older software patterns like daemons. However, the dominant way of deploying a replica is to define the replica options in your deployment, and that's what we'll do today. We'll focus on the first as is the most common, robust, and useful. Don't worry about the details of the others. We only mention them to be complete, as you may encounter them in documentation, discussions with others, or elsewhere as you explore Kubernetes and need to address more advanced niche use cases. Let's look at something familiar, our Tomcat server from previous lectures. Remember our Tomcat server deployment and when we said that we'd come revisit a few of the other parameters? Well, let's example the line that says Replicas 1. At the most basic level, this is where we declare to Kubernetes how many copies of the pod we'd like to run. We can run as many as we have resources for on our cluster. There are various other properties we can set to define how these replicas are built, where they can run, and the like. But for now, let's keep it simple and simply tell Kubernetes we'd like to run 4 replicas and leave the rest to Kubernetes itself. By setting replicas to 4, we have specified for this deployment that we'll have 4 replicas of the Tomcat pod running. This can provide redundancy and more capacity in a properly architected application. We could either create an entirely new deployment that looks like the above, or we could use a Kubernetes scale command to scale our existing deployment. Let's look at that. Issuing this command to our existing Kubernetes deployment modifies the deployment to have the exact same effect as if we were to make a new deployment, but it saved us from the headache of having to delete our old deployment and create a new one. It's also avoided any downtime for the application during that switchover. The Kubernetes CTL scale command will set our existing Tomcat deployment to 4 replicas. Let's run this against our existing Kubernetes deployment and see what it does. If you had stopped Minikube the last time you'd used it, remember to start Minikube by issuing the minikube --start command. I already have it running, so I won't execute it. Let's use the Kubernetes CTL scale command. Let's type Kubernetes CTL scale --replicas equals 4 deployment / tomcat -deployment. Let's execute the command to scale our Tomcat deployment to 4 replicas. At this point, you can trust that Kubernetes has scaled the Tomcat deployment given the output from the command. Or you could use a number of commands which you're already familiar with. For example, the Kubernetes CTL get deployment command will get the information about the Tomcat deployment. You can see here we successfully have 4 up-to-date replicas. You could also use the Kubernetes CTL describe deployments command to get more detailed information about the nature of these 4 replicas. You can see from the output of this command that Tomcat deployment was scaled to 4 of 4 replicas just a few seconds ago. So, now that Kubernetes is running 4 replicas, how does it decide which one gets to do the work? That's the second half of scaling. Now that we have 4 replicas running, we'll need to update our service definition connected to our deployment to take advantage of our replicas. You may recall from previous lectures that the only way pods can be exposed to the outside world is through defined services. We have used the kubectl expose command to create services to expose our previous Tomcat deployment to the outside world using the node port service. This command created an external port that connected to the port running on the pod that ran the Tomcat container. It mapped one port to one service on a node. That's what a node port service does. Now that we have multiple nodes running the same service, we need to graduate to something that can handle something more sophisticated than just exposing a single port on a single node. You may recall from the previous lecture that the load balancer service provides exactly this function. A load balancer is a type of service that exposes a single port, but uses a variety of internal logic, which we'll cover later, to decide which replica to send the request to. Let's look at what a load balancer service will look like for our Tomcat replicas. As you can see, it's not that different. We've added a few more options to set the newly created service's name to something predictable, and define the port we'd like to listen on and what port it's going to be on the pod. First, let's use the kubectl expose deployment command. Using this command, we will specify that our Tomcat deployment should have a load balancer exposed on port 8080, forwarding to port 8080 on its container and all its replicas, and we'll give it a name, something that we can easily refer to it by later. We'll see the command was successful when we can see that the service was properly exposed. Finally, we can use the kubectl describe services command to give us more information about the newly created service. Specifically, we can see what IP address was issued for the newly created load balancer. Let's issue the kubectl describe service tomcat-load balancer command. Remember, that's the name we gave it when we created it. As you can see, it's assigned an internal IP. Since we're running on Minikube, this will be an IP that we probably can't access. When running on a production cluster, it will be available as an external IP from whatever APIs your cloud provider may provide. For now, let's not worry about how we access the load balancer. We'll get into that when we talk about the DNS system and how names and network addresses are resolved in your Kubernetes cluster. For now, simply be confident that the load balancer was properly created, and since we're running on a Minikube, there's some things we're just not going to be able to get. Like an example, load balancing. We'll cover these items in later lectures. Hopefully, by this point, you're getting the feeling that deployments are pretty central to things in Kubernetes. We've used them to define a Tomcat service, scale it to multiple pods, and tell a service how to access the pods inside our deployment. As a foundation for diving deeper into Kubernetes, let's discuss more about deployments, their nature, and how to work with them. Deployments are a way to declare a desired state for your application. Kubernetes uses your deployment, usually defined in a file, to deploy your application according to how you describe it in your deployment configuration. You've already worked with a couple basic deployments to define a Tomcat container and then scale it. Deployments give us the advantage of letting us describe the semantics of our application and its needs in a central area, and let Kubernetes handle a fair amount of the details for us. They're not the only way of deploying applications to Kubernetes. In fact, in earlier versions, they didn't even exist. You had to work with the lower level objects, for example, the pods, the containers, the images, yourself, and create your deployment the way you wanted it. However, they have become the de facto standard and insulate you from having to handle otherwise quite complicated tasks on your own. With deployment objects, you can do a variety of things. You can create a deployment, you can update an existing deployment, you can apply rolling updates to pods running on your cluster, you can roll back to a previous version, or you can pause and resume a deployment. We've already done the first thing on the list. In fact, we've already done the second as well, when we set the existing deployment to a replication factor of 4 in the previous lecture. Applying rolling updates is very useful. We can use deployments to ease the pain of updating an application. By using rolling updates, we can use Kubernetes replication function to only update a subset of our replicas at any given time to a new version of our application, so the upgrade could occur without any noticeable downtime to the user in a properly architected application. We can also use a set of functions to roll back to a previous version of a deployment. If an update caused a problem, or for any other reason we'd like to go back to the previous version of an application, we can use the deployment rollback feature to go back to a previous version. And finally, you can pause or resume a deployment. And this is exactly what it sounds like. The application running as part of the deployment can be paused or resumed with some simple commands. Working with deployments is equally simple as many other things using kubectl. kubectl is your gateway to working with deployments. Here's the useful commands and what they do. First, you can list deployments using the kubectl getDeployments command. Then, you can also view status of deployment rollouts using the kubectl rollout status command. You can also set the image of a deployment using the kubectl set image command. And finally, you can view the history of a rollout, including previous versions that you're able to roll back to using the kubectl rollout history command. Let's go through each one of these commands in detail, and you can follow along. We'll start off with one that you're already familiar with, kubectl getDeployments. We've used the getDeployments command to see what's been running on our minikube before. By typing kubectl getDeployments, we're able to see what is running and a variety of information about it. In this case, Tomcat deployment has 4 replicas. We can use the rollout status command by typing kubectl rollout status deployment and the name of a deployment to see the status of a deployment and if it's been rolled out. Once the command is executed, it'll tell us if it's been successfully rolled out or not. Let's refresh our memory on what our Tomcat deployment looks like. Let's look at the deployment file. In this file, you'll notice we specified one container, named Tomcat, using the container image Tomcat:9.0. This deployment has one container, the name is Tomcat of that container, and it specifies the Tomcat:9.0 image from Docker Hub. We could use the kubectl set image command to change the image in any container, as long as we know its name and the new image that we'd like to set it to. Let's upgrade to the newest version of Tomcat, 9.0.1, using the kubectl set image command. To do so, we'll need to note the name of our container and the name of our deployment. With that information on our screen, let's use the kubectl set image command, specifying our deployment, deployment/tomcat-deployment, the name Tomcat for our container equals Tomcat:9.0.1. That will set the image name on the Tomcat deployment. Let's execute the command. As you can see, the deployment was successfully updated. The kubectl rollout history command can give us information about the history of a rollout of a deployment. In this case, let's specify kubectl rollout history deployment/tomcat-deployment to get the history for our Tomcat deployment. As you can see, it'll note we've made 2 changes recently. We can get the information and the details of a given revision by typing the same command with the --revision equals the revision we'd like to look more information about. Let's look at number 4. As you can see in this situation, it's given us the information about what the state of that deployment looked like in that revision. As your Kubernetes deployments grow, you'll have more and more objects available to you in the Kubernetes interface, both in the command line and on the web. Don't worry, we'll get into the web interface later. There are a variety of tools that are available to you to organize items within the Kubernetes interface. These are called labels and selectors. However, labels aren't useful just for organizing for the end user. Labels can be used to describe to Kubernetes how various objects and resources within the cluster work together. As your Kubernetes deployments grow, they'll invariably include multiple services, pods, and other resources. Keeping track of these can become cumbersome. Even more challenging can be describing to Kubernetes how these various resources interact, how you want them to be replicated, scaled, and serviced, and what to do and to what object when things might go wrong. That's where labels and selectors come in. Labels are key value pairs that let you set human-readable attributes on nearly any resource. Selectors are the criteria you can use to match labels. This way, using labels and selectors together, you can begin to describe to Kubernetes how your system is configured. Kubernetes also provides a few labels out of the box for common concepts. For example, things like hostname, operating system type, architecture, and the like are defined on nodes. A complete list of the predefined labels is available in the Kubernetes documentation. Let's work with an example of how we use labels and selectors to accomplish a task in Kubernetes. For example, let's say we had a deployment, and we had a variety of nodes in our infrastructure. But only one of these nodes had an SSD. All the others were spinning disks. We have an application which requires an SSD for both speed and consistency. We can use labels and selectors to describe to Kubernetes the variety of traits about our nodes. We'd apply labels to each node, indicating whether they had an SSD or a spinning disk. Then, we could use selectors to tell Kubernetes that when it's deciding what nodes to run a given pod on, to only use nodes that had a label SSD. Labels and selectors together are not only good for organizing for a human in an interface like Kubernetes CTL or the web. Labels and selectors allow Kubernetes to make decisions based on logic that you describe to it in the deployment to do real, actual tasks in scheduling and error recovery. You can label nearly anything in the Kubernetes world, whether it's deployment, services, nodes, or anything else that's addressable through the Kubernetes ETL interface. Let's use labels to label a node that has SSD storage, and then use a selector to tell the deployment that our application should only ever go onto a node with SSD storage. For this example, we're going to use node selector. Node selector is a property on a deployment that uses labels and selectors to choose which nodes the master decides to run a given pod on. To accomplish our goal of running our deployment only on nodes with an SSD, we will first label a node as having an SSD. Then we'll define the node selector on our deployment to match only nodes having the label we just defined. The first order of business is to label our node. Let's use the Kubernetes CTL get nodes command to find the names of our nodes. Since we're running on a minikube, there's only one, predictably named minikube. Let's type Kubernetes CTL label space node space minikube to specify we'd like to label the minikube node. Then let's tell it we'd like to label the storage type equals SSD on that node. Once this is set, we can use the Kubernetes CTL describe node command to look and make sure that our label was set. If we scroll up, we can see that the label was successfully applied. Now that our label has been applied to our node, we'll need to apply the node selector to our deployment. Let's go look at the deployment.yaml file. Remember, this is available in GitHub under the labels and selectors directory. The deployment.yaml file looks pretty much like we have throughout this course, except we've added node selector with storage type equaling SSD. This tells Kubernetes that when it's selecting nodes to deploy Tomcat onto, it should look for a label named storage type with the value SSD. Since we've made a change to our deployment.yaml file, we'll need to use the kubectl apply command to apply that change. Let's make sure that we're in the proper directory and look at the deployment YAML file to make sure it's the right file. Looks good to us. Now let's use the kubectl apply command with the -f flag and pointing to the deployment.yaml. This will apply the new updated deployment.yaml file onto our Kubernetes cluster. As you can see, the deployment was successfully configured. Using the kubectl apply command allows you to apply changes to the deployment that may not be possible using a variety of kubectl commands. For example, node selector must be done in the deployment file. Kubernetes is smart enough to understand what changes need to be applied and what is different from the new application of the deployment from the existing one. With this change applied, Kubernetes will only deploy Tomcat to nodes that have been labeled with a storage type equaling SSD. So far, we've assumed everything is going well in our software world. We've built a Tomcat service, scaled it, and even put it behind a load balancer. But what happens when one of these replicas has a problem? A bug in an application takes it down, or an issue with the runtime hangs it? How do we detect that? Kubernetes defines a variety of ways of doing this. They're called health checks or probes. They are what they sound like, a way of telling Kubernetes how to check the health of a given pod. Kubernetes has two types of health checks to ascertain two different things. First, Kubernetes uses readiness probes. Readiness probes are, well, what they sound like. Kubernetes uses them to determine when a pod is ready. After it has started the container, it can use a readiness check to see and ensure that that container is ready for work. Liveness probes determine when a pod is healthy or unhealthy after it has become ready. Whether it's a readiness probe or a liveness probe, you can use a variety of methods to ascertain a container's status. You can create a probe, whether it's for liveness or readiness, that uses HTTP or TCP to send a request to the pod. If it succeeds, it's deemed healthy. If it fails, in the connection or an HTTP error code is sent, it's deemed as a failure. Or you can specify a command to run on the pod inside the container. If that command exits normally with a 0 exit code, it's deemed a success. Anything else is deemed a failure. These probes, whatever they are, whether they're HTTP, TCP, or execution of a command, are defined on the container in a deployment or a pod specification. Let's go back to our Tomcat deployment to define a readiness probe and a liveness probe. The first thing we'll do in our example is that we will use a readiness probe to check whether the pod has started and is ready to begin taking requests. Most basically, we're just checking to see if Tomcat has started up, since this might take a while on some machines. Finally, once the readiness probe has indicated that the container is now ready to do work and accept work, the liveness probe will begin on the Tomcat deployment. That will begin to check at a given interval if Tomcat is accepting requests or if it's hung. From the GitHub repository, let's look at the basic and core concepts /health checks directory. The deployment.yaml file located inside it is what we're looking at now. You can find this file, again, under basic and core concepts /health checks in the GitHub repository. Take a moment to open it if you need. You'll notice it looks pretty familiar. The file, up until about a little bit more than halfway down, looks exactly the same. We've added two stanzas, the liveness probe and the readiness probe. You'll notice that these two stanzas have a lot in common in themselves. In fact, the way you define a liveness probe and a readiness probe, the actual format, is exactly the same. You'll notice a few differences in a few of the properties within each one. That's because we need them to do different things. Remember, the readiness probe at the bottom of the file is our way of telling Kubernetes how to test to make sure that when it starts the pod, that it is ready for work. In this case, we'll tell it to access port 8080 every 3 seconds after an initial delay of 15 seconds on simply the / directory. Once this succeeds, Kubernetes will know that the pod is ready for business. After that, it'll go to the liveness probe. Every 30 seconds, after an initial delay of 30 seconds, it will use HTTP to access port 8080 on the / path. If the HTTP request fails, it will deem the pod to be unhealthy. We'll go over what happens later. If the HTTP request succeeds, it's deemed to be healthy. Let's begin by checking to make sure we have the right deployments file. From the health checks directory, let's look at the deployment.yaml file. A liveness probe and a readiness probe. Looks good. Let's use the Kubernetes CTL apply-f command and pointing to our deployment.yaml file to apply the contents of it to our cluster. Once it's applied, let's use the Kubernetes CTL describe command by specifying deployment, tomcat-deployment, to look at the details. You'll see this output looks pretty similar, except now we see a liveness and a readiness line. These are our indications that a liveness and a readiness check has been deployed as we thought. Up to this point, our primary point of contact with Kubernetes has been the Kubernetes CTL command-line interface. Kubernetes CTL continues to be the dominant tool and will be for the remainder of the lectures. However, in some situations, a web interface is equally useful. Kubernetes provides a web user interface called the dashboard that we can use to access the same information that Kubernetes CTL can present in a friendly point-and-click web interface. It's called the dashboard UI. It runs on your Kubernetes masters and is accessible directly if you have a direct connection to your cluster or to your masters. This is unlikely in production situations. However, Kubernetes CTL is your friend. Kubernetes CTL can create a proxy or a tunnel for you from your local workstation to a Kubernetes cluster that you may not have direct network access to using the Kubernetes CTL proxy command. The Kubernetes Web UI, or the dashboard, provides a variety of views for nearly anything in your Kubernetes cluster. It allows you to update, delete, and create nearly anything you may need to in your Kubernetes cluster as well. It accesses the same APIs as Kubernetes CTL. It simply provides the interface and the data in a different form. Using the web interface is quite simple. On some Kubernetes clusters, the dashboard UI is pre-installed. Most cloud providers automatically install it when you provision a Kubernetes cluster on their managed services. However, if you're bringing one up from scratch, or are working with a provider that doesn't enable this by default, you can use the Kubernetes CTL create command by installing the dashboard using the command shown. You can access the dashboard through a variety of ways. As we mentioned earlier, if you have direct network access to the IP address of your Kubernetes masters, you can simply go to the web browser and go to http:// the IP address or the host of your master :8080/UI. However, the most foolproof way and the recommended way, even if you have direct access to the masters, is to use Kubernetes CTL proxy to set up a proxy on your local machine that will access the API and the interface remotely through a tunnel. Type Kubernetes CTL proxy and navigate the localhost :8001/UI in your web browser. Let's start the service by typing Kubernetes CTL space proxy. You'll know it's successful when it says starting to serve. Note the URL. We'll use that URL to access the web interface on our machine. Let's take this URL to our web browser to access the Kubernetes dashboard. You're welcomed by a variety of information. The overall status of your Kubernetes cluster, how many pods are running, what pods those are, what deployments they belong to, and the replica sets automatically created for us in those deployments. This should look familiar. This is largely the same information that we were able to access using the Kubernetes CTL git deployments command. These are the details of our Tomcat deployment. You can access a large variety of information through the Kubernetes web interface. A number of objects are available, many of which we haven't discussed. Don't worry about the details of those yet. One of the objects we have discussed, however, are nodes. Everything we're looking at in the Kubernetes web interface runs on a node. So let's go check out our nodes in our minikube. Remember, since it's a minikube, there's only one node. Let's look at its details. We can browse through the various information that we would have gotten if we had used the Kubernetes CTL describe node minikube command. It's also providing us with information about the resource, what pods are running on it, and a variety of other information. You'll even notice that the label set, storage type SSD, in a previous lecture is available and shown here, much like the output from Kubernetes CTL. In fact, this data comes from the same source as all the data from Kubernetes CTL, just another way of getting to it. Similarly, operations available to us in Kubernetes CTL are also available to us in the web interface. By clicking the Create button, we can create a deployment. This offers us a graphical user interface to the same information as we would have defined in a deployment.yaml file. It's up to you whether you'd like to use a what you see is what you get WYSIWYG style editor as you can see here, or use the power of the command line and your own YAML text files. If you choose to use your own text files, you can still upload them with the web interface. This is the functional equivalent of using the Kubernetes CTL apply command, which we have in previous lectures. To learn more about Kubernetes, we encourage you to come back to take the dashboard tour to learn more about each individual item and action you can take and view within the web interface. For now, simply knowing that Kubernetes CTL and the web interface are available to you as two methods of getting at the same data and viewing or manipulating objects in your Kubernetes cluster is enough. Picking the right tool for the job is always a way to be most effective as possible. Kubernetes CTL excels at certain things, and the web interface excels at many things. Now that you have both tools at your disposal, you're able to choose what is most effective and what you may prefer. By now, I hope you're getting an idea of the variety of tools available for you in deploying, scaling, and monitoring applications on Kubernetes. Don't worry if you don't feel like a master yet. Kubernetes is a sophisticated software system, and even the most experienced professionals take time to adapt to its ways of doing things. In this exercise, you'll leverage what you've learned to provide a solution to a given set of success criteria. What you've learned to this point includes how to define a deployment in Kubernetes, how to deploy this deployment to Kubernetes, and how to scale this deployment. We've gone over a number of other things, so this isn't an exhaustive list. In the lectures to date, we've gone over a variety of commands that will help you deploy, manage, and examine your cluster. Think about the variety of commands we've used, and perhaps even go back and review previous lectures to understand what commands might be available to you. Your task is to use what you've learned to deploy and scale MongoDB. MongoDB is a popular NoSQL data source. It in and of itself can be quite complicated, but your task here is quite simple. Just take the default installation of MongoDB and have it running on your Kubernetes cluster. The success criteria will be that the current version of MongoDB is up and running on your Kubernetes cluster with 4 replicas. We're not going to tell you how to do it, but we'll give you a few hints. First, you should know that MongoDB listens on port 27017. In its default configuration, this is the only port that Mongo listens on in a single node configuration, and that's what we're going to use, Mongo out of the box. Another hint is that you can find officially supported MongoDB Docker images on Docker Hub. These couple of hints and the information that you've learned in the lectures to date should be enough to get you going. Now it's your turn. Come back when you're done and see if your solution matched ours. And remember, it's okay if it doesn't. Kubernetes has multiple ways of going about the same work. Whether you use commands or you use deployment files, there are multiple ways that you could achieve the end goal. We'll see you back here when you have a solution, and we'll review one possible solution and a few others. The solution we'll review uses only two commands. First, it uses the kubectl run command to run the default Mongo image from Docker Hub. It also includes a directive to expose the 27017 TCP/IP port that Mongo exposes by default. Once that's running, it uses the kubectl scale command to scale the deployment that was just created using the run command to 4 replicas. At this point, Kubernetes will have downloaded the image, created the default deployment, and exposed a port, and scaled the service to 4 replicas. Let's run the kubectl run command, specifying a name, an image to run, and a port to expose. At this point, Kubernetes will pull the image and run a default deployment. Now, let's use the kubectl scale command. The kubectl scale command, remember, will take the name of the deployment and how many replicas we'd like to apply. Looks like I forgot the dash in front of replicas. Let's fix that. At this point, much like we've done before, it's scaled to 4 replicas, but let's check anyway. We can use the kubectl describe deployment command. You can see that the replica has been scaled. Don't worry if there are some unavailable as of yet. It takes a while for those replicas to start up. If you run this command again, you'll see that they're available. Of course, as we mentioned, there are other ways of going about this. You could have written a deployment.yaml file, applied that to your cluster using kubectl apply, and used kubectl expose to expose the port 27017. You could have written a deployment.yaml file and a service.yaml file to describe the service, and use kubectl apply on both to apply them to your Kubernetes cluster. Finally, you could have also used a Kubernetes package manager, such as Helm, to handle the work for you. Now, this third one's definitely an advanced usage, and one we haven't gone over yet. But towards the end of the course, we'll look into third-party tools that will make you more productive. But the goal now is to understand exactly the internals of Kubernetes and the kubectl command line. It's worth noting you could have also used the web interface in lieu of the kubectl commands with possible solutions 1 and 2 to achieve the same result. You could have written these files and uploaded them using the web interface, and then used kubectl to expose a service if you chose. Whatever solution you chose, or perhaps you found another way of achieving the goal, the important thing is to remember the tools in your toolbox and how they fit together. Then, understanding the basic patterns of how to use kubectl and how Kubernetes objects interact with each other. If you know the foundation of these, as you practice, you'll grow into a critical thinker, able to do a variety of tasks in Kubernetes without consulting documentation or higher level architecture.